Alright, recognition theories. So we talked last time about the binding problem. So how do we take all these things in our visual field and put them together? So the whole thing is called recognition. It's the idea that we have all these representations. Remember, representations are physical pieces that represent something. So that can be a neural message, it can be a stop sign. Remember, it's got that very vague definition to cover inside and outside your head. So we're going to take the information coming in through sensation and match it to something stored in memory to help us recognize objects. So how do you know that your phone is your phone? It's because you have a memory of your phone and you're seeing that visual picture that matches that memory. Okay? But the coolest way to study things that work for cognition is to actually study the times that it doesn't work. And that really gives us a good picture of what's going on when we can figure out times that it doesn't work. Okay? So that's called agnosias, sometimes called aphasias, but in this case it's an agnosia. And so this is when there's damage in the brain, but not to the sensory organs. So there's nothing wrong with the sensation, it's something wrong with perception. So when your sight is fine and recognition is not, it's called visual agnosia. There's two types. Aperceptive agnosia, which is the inability to recognize simple shapes. The way I remember this one is that is a complicated word to spell, and so it's the opposite. It's a simple one. So aperceptive agnosia is the simple shapes problem, like squares, triangles, rectangles. Associative agnosia is an inability to recognize complex objects. So I can't associate what those simple pieces are to the more complex picture. Let's give you an example. So drawing from a patient with associative agnosia, so they're drawing the anchor here. They could draw it for you, but could not tell you it was an anchor. They could tell you that the anchor's parts were made of triangles and rectangles, but wouldn't be able to tell you that it was an anchor because they can't recognize complex objects. So why does this happen? What is it about recognition? So 4 theories for recognition. And the third one's a little odd. So we've got template matching. It was the first big theory for recognition. Feature matching will make a reappearance in the category learning section. Recognition by components and configural models. So really in each of these, think about what they're trying to explain because they each had different purposes. So they were attacking recognition from different angles. So template matching models are probably one of the most popular ideas because it just makes sense. So a template is a stencil, the way it looks. So your image of an apple, you have a picture for that in your head. Okay, so in template matching, what you do is you take the item that you're looking at and you take your template for that item and you say, look, they match, or no, they don't. It's very similar to the idea of like a barcode or a fingerprint. So it helps if it's one-to-one because then your template and your picture, they match perfectly. I can recognize things. Okay, here's the problem with that theory. If I have a match that I'm trying to figure out between A and L, look how complex these templates are for the different versions of the letters. So an even better picture. If I'm trying to match A's that are written all differently, so let me see here, especially this piece down here at the bottom, I can see that my template is okay for this first one and slowly gets worse. So if template matching theory were true, we would have to have a separate template for every size, variation, and viewpoint, and that's not very economical. Remember, one of the very first rules from this section was we don't like to think hard, and that is way too hard for us. And so we don't want to use a theory that doesn't match what we actually do. Okay? And then I have a slightly repetitive part here, sorry. A lot of computer programs use this, so things like Siri, which try to match the sounds, the component sounds to specific words. You know how well that works because of accent or how fast you're talking. We've already mentioned barcodes and fingerprints are really good for template matching, but things like language doesn't really work. So what do we do? Everybody sort of stopped using template matching theory and moved to feature matching theory. So instead of having a one-to-one template, what we've got is a set of features that we have to have. So like simple but characteristic features of the object. And if those are there, that's a match. And so the issue with that is what are the features? And so it just depends. So things like robins have to have wings, they have to fly, they have to have feathers, they have to sing for them to be robins. And it really matched the brain. So remember, this is converging evidence that everything happens in parallel. So all of those features are getting detected at the same time in different receptive fields. And that's the distributed part here. And they're all happening at the same time. That's the parallel part. And then we take it and put it all together. So feature matching theory better match the brain as well. So here's an example of a really complex feature matching theory. This is a neural net model. So remember, those are the ones that try to explain how our neurons work. So this bottom level here are very simple edge and bar detectors we talked about earlier. And so when those come on, or they light up, or they activate, they feed into the letters. So anything, this is really tiny, but anything with a little arrow is a positive activation, meaning that this piece is part of the letter A. Anything with this little dot is a negative activation. So the straight line here to the A is negative, as in if I see the straight line, I know it's not an A, but it would be an N. So that brings up the letter perception, because we don't sense letters, we perceive them, because we made them up. And then those play into our word perception. So A would be good for able and trap, but if I see an A, I know I can't have time, so time would be marked out. So this is called the parallel distributed process for word perception. It's one of the first and most popular neural net models for understanding our language processing. So the good thing about feature mapping theory is that it really has less storage space. It's more economical. We don't have to have one template for every different version. We can have just a list of characteristics that are important. And the feature detectors are actually what is in the brain. The complicated part for feature matching theory is that sometimes it's difficult to tell what those characteristics should be. And so for example, if we're talking about birds, most people agree on the flies and the wings and the sings part until you ask them about penguins. And that tends to throw things off a little bit because they do none of those things. The third theory, completely separate, totally different question, was trying to explain 3D perception separate from all that Gestalt stuff. And so it's called recognition by components. It's an understanding of three-dimensional objects and really thinking about a viewpoint for things that aren't flat. And so three-dimensional objects can be broken down into these things called geons, which are simple three-dimensional shapes. So we're still breaking things down into feature components, but we're going to call them geons now. And the funny thing about geons is they're a little silly. This theory is not super popular anymore. So this thing is a horse, so it's broken down into all these different cylinders. Us people here are the long leg cylinders, but we've got the same legs as ostriches. And giraffes' legs are just a little bit longer than ours. So the idea would be that we would say that horses and giraffes look similar because they have the same geon shapes, whereas doves and ostriches are similar because they have the same geon shapes. If that sounded ridiculous, that's because it is, and most people don't think about it that way. So here's some other examples of the different types of geons that you would have. So clearly something's going on because we have a wine glass example, which is not in 3D at all. So the Geon theory is not super popular anymore. Recognition by components was just a different type of feature matching theory for 3D objects. And then some support for the theory here was that if you had the 3D components in the right order, people could tell what they are. And sometimes if you had them close enough, they could tell that, yes, this is still a telephone. But one problem I have with this particular experiment thinking about 3D geon theory is that these are actually not geons. This is totally flat. So how are we actually measuring the fact that people see in 3D with 2D pictures? So, you know, the theory's not being used much anymore. It's got a lot of problems. The last one is configural model. And configural models are for faces. And so it's really played into prototype theory, which you'll see again when we talk about categories. And the idea is that there is a prototype or a perfect or an average example instead of a set of feature characteristics. And it's really about spatial relationships and very much about faces. So they help us understand our face recognition. So as long as the pieces are in the right place for faces, we can recognize them. And so when things deviate from a prototypical face, we talk about how things are unrecognizable or unique or different somehow. So some issues with face recognition. I'm going to try. I think it's prosopagnosia. And that is the inability to recognize faces. So we've kind of talked about this before. This is the Oliver Sacks book, The Man Who Mistook His Wife for a Hat. And that is a problem with the fusiform gyrus. Remember, that's in the temporal lobe, which also does memory, and so it's an inability to recognize faces. So what we can do to test this theory is take a prototypical face here in the middle. This is our average face. And then what we do is we train people, or we show them a non-prototypical face, so either end here, and we have them look at it for quite some time. And then once they look at this picture for a while, we show them this middle face, or the other way around, and ask them how the middle face looks. So you can change what is considered average by looking at a non-average picture for a while. So if we ask people to look at the faces on the ends for quite some time, the face in the middle no longer looks average. Now if you think about the issues going on with perceptions of beauty, especially in our culture, and the way that things get photoshopped, especially in women's magazines, the perception, if we look a whole lot at those types of images, it can change what we would consider average or normal. And so it's often confusing to people to think that the size 2 is not normal because you see so much of it. And that is because we can adapt people to specific different what we would consider average, because you see it more often. Okay, so how this applies to your everyday life. Alright, so all that's bottom up processing. Let's switch and do a little bit of top-down context. So most recognition theories start bottom up. So what happens when we do top-down? Okay, remember that top-down is using the background knowledge of the world to create our perception. And so not everything is about just the features. Often we're going to use things called heuristics that will come back when we get to problem solving, which is just sort of a shortcut. Heuristics are considered rules of thumb about making sense of the world. The other big component for heuristics is this inferences thing. So we don't want to think very hard, and we want a quick and dirty answer, and that's where heuristics comes in. And so we can see what people's top-down contexts are by sort of screwing with them with visual illusions. which is also part of the next module. So, if I'm going to talk about recognition and do top-down contexts, we have sort of an expected context. So recognition is faster if it's something that you expect, or if it's something that is normal, so customary. Recognition can be bad if the context is unexpected, so if it's a surprise, right? And then if it's inconsistent. So things that are normal or usual or average are fast. Things that are new and different are slow. Alright, so if I'm looking at this picture, this was taken at Texas Tech where I did my graduate work. This is in the library, or it was. And I'm talking about studying, you've got an exam, books. You'll see this as a bunch of desks, right? So I'm going to study here, put my laptop, I'm going to write a bunch of things, think really hard. But if instead we were talking about World War II, you would see it as a swastika. So the desks in the library at Texas Tech are shaped like swastikas. And so the perception of what's going on in this picture changes based on which context I gave you. That's top down. The other fun thing you can do is, well, like I said, with visual illusions, this is called the devil's pitchfork. Because it's an impossible figure. Actually, all of these are impossible figures. If you follow this nut around, you see that the middle and the front are the same, which is impossible. Or if you try and follow the front of this around, you realize the front and the bottom are the same. So impossible figures sort of look realistic because the context-wise, they should sort of work, but they don't. Alright, face perception. Sometimes I can get this to work, sometimes I can't. If you click, nope. Alright, well, okay, so face superiority. The face here is in the right order, right configuration. Here, the eyes and the mouth are still right side up, but the face is upside down. It tends to really creep people out. I've got some more examples in the illusion section, but face superiority, we like faces to be in the right order. The most important for top-down context is the word superiority effect. This is that thing that you see on Facebook where people have scrambled the letters in the word and say, as long as the first and the last letter are there, you can read it, A+. And that's true. We do like things to make actual words. So we can read words that are scrambled or misspelled because of our expectation of what is supposed to be there. Okay, so this is the famous picture. Given that you're looking at it this way, it's the word cat, and that's an A. Given that you're looking at it going down, it's the word the, and that's an H. So different perceptions from the same sensation based on our expectation of the way that words should be spelled. Okay. So in summation for this section, we don't like to think very hard. So expectations are the important part for top-down context. And so here's some examples of expectations and how they influence us. Brightness expectation is the idea that if I were to turn off the lights, I'm still the same person talking, and you can recognize me because even though the brightness has changed, you expect me to stay constant. I don't suddenly turn green. Size is really about, if you think about cars, so as cars come over the horizon, you don't suddenly freak out and go, oh my god, that car's getting so huge, it's Godzilla. Your brain just thinks it's getting closer to you because it's getting larger in size. So we expect cars to not morph sizes in the middle of the road, and so we interpret that as distance rather than size changes. Shape changes are as things move around, or you see them from different perspectives. They're the same object, we're just viewing them from different directions, so the shape doesn't change. Color and brightness are the same idea. Even with the lights off, my shirt is still black. So in conclusion, before we move on to the fun part, which is illusions, sensation and perception interact. we started with sensation was too much and too little information to fully explain perception. And so we have to think about both of them, because sometimes it's bottom up, sometimes it's top down. So we have to think about the featural level, that's the bottom up, and the context level, which is top down.